morning, everybody. So the title of my talk, it's towards model-driven TES, and what you have here in this slide, it's a display of the technologies that we have in our company. These are multi-electrode systems for wireless EEG and wireless brain stimulation, transcranial brain stimulation. And our devices can work with up to 32 electrodes for either EEG or for TES. And the question that we will be discussing today is how can we use this controllable technology in order to treat epilepsy. Next slide, please. So currently we have a pipeline in place in the company. The company started about 10 years ago. And from the very beginning, we realized that to handle this powerful but complex technology, we needed to develop models of what's happening. So right now we have in place a pipeline that allows us to start from the MRI of a patient, a target defined by a neurologist. And with these pieces of information, we can construct a realistic head model of the patient to model the flow of currents in the brain and to create the electric fields that we want to deliver to the target, and also sparing parts that we don't want to interact with. And so in the pipeline, we receive this data, we process it in roughly in less than a day, and we are aiming to currently reduce to less than an hour. And we output a personalized treatment protocol for the patient. Okay, so this is the TES 2.0 pipeline, as we call it, for focal epilepsy and other pathologies that I will not be discussing today. Next slide, please. This technology was, we tested it already in an open label trial at Boston Children's Hospital with one cycle of stimulation. So the protocol consisted of a baseline of 8 weeks, treatment of 2 weeks with TDCS, cathodal TDCS over the target specified by the neurologist, and then a follow-up of up to 3 months after that. And this study was, our PI was Dr. Alex Rothenberg from Boston Children's Hospital. Next click, please. The outcome was this change in seizure frequency from baseline for these 17 patients that completed the study out of 20 that started. Next slide, next click, please. And a 47% responder rate, usually treated as people having more than 50% reduction, with a 47% median seizure frequency change, and the results are published in this paper here. Next one, please. We have currently replicated and extended the study at Marseille with my colleague, the PI Fabrice Bartolomé. This is a similar study, again open label, with 10 patients. This time we did 3 cycles of the technologies of the treatment. So we basically had one week of treatment in which 2 sessions were delivered during the same day, and then a follow-up of 3 months, and this was repeated 3 times. Next, please. And as you can see in the top plot with this, well, the mean seizure rate reduction was 48%, 50% responders. And in this group, the seizure reduction was 74%. And on the bottom, you can see the non-responders, which we also had, of course. Next, please. So we have started recently a pivotal trial, an FDA Monitor pivotal trial, which will last about 3 years with 190 patients with medical refractory focal epilepsy as the previous 2. And it's a multi-center study. Again, our PI is Alex Rothenberg from Boston Children's. The treatment will be similar to the previous open label studies with 20-minute sessions over 10 consecutive weekdays. With personalized stimulation montages for each patient based on the MRI and the specification of the neurologist for the target, 12-week baseline, 2-week treatment, and 10-week post-follow-up period. And the primary endpoint will be the change in seizure frequency over the 12-week baseline versus the 10-week post-treatment period. Next, please. So I want to tell you briefly about our the research that we're carrying out in the modeling team at Neuroelectrics, which is we call TES 3.0. And this is patient-specific personalization that goes beyond the physics. So we start from subject data, which now includes not only MRI, but also SEG as available, DTI, DMRI for the connectomics. And with this, we construct first a physical model of the patient's head, but we also deploy a physiological brain model based on neuron mass models connected with the connectome, which are personalized and adjusted using data from the patient from EEG and SEG. This, we call them neurotwins. This neurotwin is used then to simulate TS treatment and to optimize it. So we no longer rely on the specification from the neurologist. We want to actually have the model tell us what is the best way to stimulate the brain to reduce the probability of seizures. So can you click again, please? So the data, once again, please. The data that we use, as I mentioned, is the connectome that we extract from the MRI. Data that can also include the location of lesions and implants in the patient's brain, in the patient's head from previous surgeries. Next, please. All this can be managed. The data from SEG, which we use then for classifying the nodes in the patient. So we have this classification currently, which we call the S classification. We have epileptogenic nodes, then we have different degrees of pathological nodes that belong to what is traditionally called as the propagation network, and then non-pathological nodes. And we, as I mentioned, adjust the models to reflect the dynamics of this network. So we try to replicate the network in silico. Next, please. Okay, so as an example of how this is about, here's an example of the personalization of the epileptogenic node. On the left, you have real SEG data with a seizure, with a fast onset and the rhythmic ictal period, and the spectral features associated with the seizure. And in the middle column, now you see the simulated SEG data after the model is adjusted. Which you can see is very similar to the real data. The model relies on, as I mentioned, neural mass models, but we have also developed a modeling of the KCC2 transport system to reflect pathological D-GABA chlorine accumulation in pyramidal cells. And combining this with the effects of electric fields on pyramidal cells, we can actually predict the effects of TDCS for these nodes. And here you have an example at the bottom of the seizure probability happening after application of TDCS of different strengths for different types of nodes from different patients. These are actually data from 4 different patients. So this is an example how we personalize the models, just to give you a taste of what we're doing. And this is available as a preprint that has been submitted for publication. Next, please. So within this particular project, which is actually partly funded by the European Research Council, the Galvani project, the goal is to have a multi-center study, which will start in a couple of years, roughly. And it will be a multi-center study with 120 patients from 10 reference epilepsy centers in Europe. We will, as I mentioned, use EEG and SEG data to specify the networks and the brain models for each patient. And similarly to the previous ones, the primary endpoint will be the % change in seizure frequency. And I believe this is my last slide. Well, my last slide is my team. This is the team that we have at Neuroelectrics for computational modeling. And thank you very much.